Oh, good afternoon, or good morning, everybody. I'm Lockie Scott, your friendly neighborhood Canadian space surveillance scientist. I'm going to talk to you a little bit today about what we've been doing in space, not just from the Sapphire point of view, but when we launched Sapphire, we actually flew the NeoSat microsatellite as well, which is a small mission to do space surveillance and asteroid astronomy. So I'm going to talk a little bit about some of the work that we've been doing in those two missions. And what I'm really going to focus on is how we tried to combine both of those satellites to work together to basically try to see what we can do to make them work in a coordinated fashion. So these are the two stars of the show. Sapphire, which is the operational space surveillance capability of the Department of National Defense. It's built on a Surrey SSTL 150 bus. It's a 15-centimeter telescope. You can see the objects down to about magnitude 16 geosynchronous orbit. The NeoSat microsatellite, it's a bit different. It's about half the size, same aperture more or less. A little bit longer baffle that we have on the microsatellite, but it's a dual mission microsatellite. It's doing both space surveillance R&D, and we're also checking for asteroids and what they call Aten-class asteroids, which are basically the asteroids that live within about 45 degrees of the sun. So that's why we have this extended beveled baffle on the front of the vehicle. Just some other notes about the programs. These were both fixed price contracts that we issued for the missions. Sapphire was actually a bit of a unique beast in that it was a government-owned, contractor-operated vehicle, and it worked really well for the Government of Canada when we implemented it. NeoSat was a government-owned, government-operated system. We found that it worked fairly well on some things. We had quite a few issues with the attitude control system, and some of which we're still working on today as we speak. And I'll talk a little bit about some of the work we've done, focusing primarily in 2015 when we had some really successful tracks with the NeoSat mission here. So I just want to dispel a disbelief, or actually a belief about going to space and tracking objects in space. There's this belief that if you go to space, you can see geosynchronous orbit continuously, and that's simply not the case. When you're in sun-synchronous orbit, the Earth gets in the way quite often, and there's actually this cone that basically sits in the anti-solar side where both satellites can basically see for about 2.5 to 3 hours when they traverse that cone. Otherwise, your observations are interrupted for a short period of time. Sapphire and NeoSat were launched on the same booster. They chase each other around orbit. They don't maintain formation with each other. They're just basically free floating and free drifting in space. And that's why you see them, there's basically a phasing that occurs. They phase in and out with each other with a period of about a year. And these are some NeoSat experiments that we've done last year. We're conducting metrics evaluation. We're tracking GPS satellites with the spacecraft. But I have to say, one of the more fun experiments we did with the vehicle was I basically tasked one of the lieutenants that works with me at Defense R&D Canada and basically said to him, I just watched the James Bond movie Die Another Day yesterday. I want you to take NeoSat and point the shiny side towards us and light us up with sunlight from the Earth. Think of it as a custom made-to-order iridium flare. And that's what we did here. It was called Project Artificial Star. And the lieutenant went out. He reprogrammed the satellite to basically reorient itself to basically glint sunlight directly onto Ottawa. And if you were sitting in West Ottawa that day, you would have saw an object brighten up to about magnitude -2 for about 4 or 5 seconds and then disappear. That was us doing that. So it's kind of cool when you get to make your own custom UFOs every once in a while. We also did an experiment with the UK DSTL. We actually tracked Skynet 5A, what it was doing, its deceleration and parking maneuvers over 95 degrees east. So it was actually a pretty interesting period. We were able to collaborate with our UK collaborators to basically try to see how well we could work together with both Sapphire, NeoSat, and other ground-based systems to do some tracking. What I'm going to talk about here is how do you combine both of those systems together, which weren't really inherently designed to work together. One of the original science plan activities of NeoSat was to basically see whether or not we could get Sapphire and NeoSat to basically try to work together in some way, just to see what it could do for doing satellite safety operations, basically trying to do experiments to see if we can reduce those covariance ellipsoids down by taking more tracking data and see if we can basically support the spaceflight safety side. So the two objects that we tracked were Anik F2 and Wild Blue 1. Both of these are large geostationary satellites. They're very well suited for tracking by small aperture sensors. Anik F2 uses ZIPS thrusters. It maneuvers quite frequently, and I'm going to talk a little bit about what that causes the space surveillance sensors to see. Wild Blue 1, it's co-located with Anik F2 on orbit, and I'll show you what that looks like here. So to basically get Sapphire to interoperate with NeoSat, I basically had to contact 22 Wing North Bay through the Canadian Space Operations Cell and get the operator, who's actually sitting over here, Tom Earl, who was to basically program Sapphire to basically elevate the tasking interval to try to track at the same time that we're tracking Anik F2 and Wild Blue 1 at the same time. And he did this basically by increasing the tasking priority on the satellite. NeoSat, we can point the vehicle to pretty much any right ascension declination that we want to take a look at in the sky, so long as we stay within the constraints of the operational needs of the vehicle. And this is what you would see if you were to do the tracks. It's a little hard to see the satellites, but this is Wild Blue 1 and Anik F2 sitting in the Sapphire imagery. And the bouncing dots that you see here are the same satellites through NeoSat. There's a bit of an odd feature that you'll see every once in a while on the Sapphire images. There'll be this little glow that you'll see in the top left of the frame. What that is the Antarctic ice sheet blasting a whole pile of light down the baffle of the Sapphire telescope. And we see exactly the same thing on NeoSat from time to time. It all depends on how close to the Earth limb that we start we start tracking the satellites. If you look away from the Earth limb, it's not a problem. So there's 3 test cases that I'm going to go over here, just NeoSat observations alone when they track the satellite, Sapphire observations alone, and what happens when you combine them. And essentially, there's 2 quality indicators that I'm going to represent, basically metric accuracy of the sensors in arc seconds, and also what the final in-track position uncertainty is after 2 days of tracks in that anti-solar direction when we're tracking satellites. And for NeoSat observations alone, metric accuracy wasn't that great. We had to run the instrument in 2x2 bin framing when we were doing this experiment. Since we're made it with an asteroid astronomy mission, we had to run the camera readout really slow. That's because you're trying to get the noise down as much as possible to allow the asteroid astronomers to see faint objects. For the space surveillance mission, that kind of runs contradictory to what you're trying to do. You're trying to take your observations at a pretty quick cadence. And anyways, as a result, in order for us to try to increase the speed of space surveillance observations, we were running the camera at 2x2 bin mode, which lowered our resolution for metric accuracy, unfortunately. And when you convert this into an orbit, we got about an in-track position error of about 4.4 kilometers, which is not bad, but it's not that great, really, just for a couple days of track. Sapphire observations alone, you'll see that the first batch of data on the first day was within 1.5 arc seconds. It's actually quite a bit better, depending on the time that it does its tracks. And the in-track position error was about 250 meters, so it's pretty good. But you'll notice that there's a lot of in-track error growth afterwards. There's a lot of observations that were being rejected. If you combine the 2 sensors together, you'll see that both Sapphire and NeoSat saw right ascension residuals walking out from one another, and the declination residuals for NeoSat, NeoSat were being accepted, but the Sapphire ones weren't. So there's a bit of a conflict that was happening here. The measurements for NeoSat, which were accepted early, kept the covariance quite large, but they weren't actually representative of where the satellite actually was. Now, when you basically fill the gap of the day side, when you can't use your space surveillance, space-based sensors to track, you fill that with a little bit of process noise to basically try to model the maneuver that occurred, which is represented by those right ascension residual walkouts, and you can basically recover the orbit enough for you to basically sustain the orbit. The problem with that is that it builds a lot of in-track error growth later on in the track. So overall, combining the observations didn't really help us a whole lot. Sapphire observations on their own would have satisfied a lot of the mission needs if we were trying to do an orbit custody experiment. Now, Wild Blue 1, the other satellite, it did not perform a maneuver during that interval. And the in-track error was actually quite well behaved to get under about 400 meters per axis, actually. And its error growth was less than, after 3 days, less than 1 kilometer. So for objects that aren't maneuvering, the space-based sensor holds the custody quite well. So can you use these space-based sensors to reduce risk for conjunctions on orbit? There's a couple of things that work against you, and I just want to show you what this problem looks like from a Canadian's perspective. Low Earth orbit, most of the conjunctions we see are concentrated over the poles, over the J2 pinch ring. We like putting our satellites in 98-degree orbits because they're thermally stable, and basically it allows us lots of sunlight to keep power on our systems. Therefore, all of our conjunctions like to converge near the poles. In geosynchronous orbit, you see that there's a whole clustering that occurs right along these fixed locations here, right around the equator. And for the inclined geostationary satellites, we see these vertical structures form out there. Now, the thing that really hits home here is that Canadian interests are actually spanning right around the world. And you might ask, well, why is that? Canada is in North America. Most of the satellites that we own, Canada owns 14 geostationary satellites, but we're actually flying 9 satellites of other countries through Telesat Canada, one of which is a Chinese company. So while we just heard a panel here a little while ago basically saying, well, are you doing military cooperation or exchange? No, the military is not, but the private sector is. So co-investment is occurring in geosynchronous orbit. So there is certainly an area where spaceflight safety has an interest in basically space situational awareness. Now, the problem with the space-based sensors to basically address risk in deep space, we usually get about 3 to 5 days for a geosynchronous warning. And the problem is that the space-based sensors take about a day to task and then maximum about 12 hours to respond with observational data. So it's not quite well matched for doing the space surveillance routine as it's currently configured. But what I do recommend is that you do task the space-based system on the non-maneuvering debris objects during flight, and basically work with a spacecraft operator to basically try to correct for maneuvering satellites on orbit. And of course, the future using northern ground stations would certainly increase the rate of certainly decrease the rate of revisit time that's needed in order to actually reduce the risk and basically collect data on a more frequent basis and try to reduce it from that daily tasking cycle that's needed in order to actually task the space-based sensors. So that's a conclusion. Space-based sensors are good for geo-chat custody, but they have a little bit of weaknesses on maneuvering objects. Conjunction de-risk is well matched, but would have to increase the frequency of ground station access to the space-based sensors in order to really add value to doing that mission on a more regular basis. And that's basically the end of my slides there. I'd be happy to take any questions you might have.
We do have time for about one question before we need to move on to the next talk, if anybody has any burning questions.
Do you think that because you were constrained to limited cone, that constrained your geometry and limited how well you could fit your orbits?
That thought has crossed my mind quite often. Observability does play a role. So the question that I am wrestling with is when you cross the equator and you look at a geosynchronous object, effectively you're doing this to yourself when you're trying to track it. Or even worse, you're looking at the same longitude as when you're tracking it. So that cone can work against you in some cases.
Right, you want to reduce your radial uncertainty to limit your long track.
That's right. Observability is a factor, and that's something I haven't really looked at here, but you are right, it is a factor.
Okay, thank you very much.
Thank
you. Thank you and welcome to my talk. Oh, where's the... sorry. I'll skip the outline and move right into my motivation, why I even perform active debris removal and develop the concept, and why I approach the way I did approach. So the ultimate goal is to have a safe space environment up there. We can only do that on the long term by limiting the amount of space debris. I do that by developing this concept for active debris removal. However, there are a few problems approaching us. We do have a close vicinity of an uncontrolled object in space. It's never easy to be handled. We do have this uncooperative target, so there is no pre-designed point of contact, was never been designed to be removed. So there's no sensors that help me to determine attitude or anything. And moreover, I cannot guarantee a flawless connection to a ground station. So in case there's a failure during my approach, the leftover drift might just end up in a collision. That's definitely what I do not want. So one idea, one solution could be, well, why not just having the satellite handling itself? Implement onboard autonomy, onboard processing. Well, it's easier said than done, let me tell you. Because you need specific applications. You can't just do copy-paste from ground. So that's why I first started with designing the mission architecture for my mission and designing the spacecraft. From there on, I will show you a little bit of the simulation I already achieved. And later on, we will implement features for a final test. So let me tell you a little bit about Address A, the active debris removal satellite, number A. There are a few requirements if you want to do space debris removal on an efficient way. We need to remove at least 5 to 15 large objects from space. Large means at least 1 ton. This again brings us to the fact that they won't vaporize during re-entry. You need to have them re-entered in a controlled way. Moreover, you want to have cost limitations, of course. So you want to have one launcher for one mission. So from there on, with this requirements, I derived my mission of having one chaser and multiple kits. This chaser will do all this work, and he will attach the kit to the target, and the kit will vaporize or deorbit together with the chaser. That's the rough idea. First of all, I looked into a target selection. There's a lot of lists out there what we should remove first, but as I said, 5 to 15, you want to be able to go from one object to another. So I'll ended up going for SL8 rocket bodies, and we are kind of lucky. They are in a few boxes. You see at 74 degrees inclination, there's 50 there, and there's 44 a little higher up. If you increase the area, you even find 120 in the area of 74 degree inclination. And if you look here at the inclination of 83 degree, you even find 144. If we say we want to remove 5 to 15, we would be busy for some time. SL8 rocket bodies have another advantage. They are owned by one owner, so one party. So the lawyers would only have to deal with this, one party. And they are also of the same geometry. So the kits I am designing and the chaser, they can concentrate on this design, and I can kind of standardize the whole process, which brings it into the hands of this cost limitation fact. I'll just go again to the mission architecture plan to have them all launched into a parking orbit, an orbit that is kind of close to the target's orbit. A kit has a weight of about 400 kilograms, so I don't want to have them with me all the time. So I leave them there while I go to my target with one kit. I attach it, and while my kit re-enters in a controlled way together with the target, I'll go back to the target orbit, grab the next kit, and I can repeat that until there's no kits anymore. You might ask what we want to do afterwards. Well, this is open for discussion, kind of. So either I bring more kits up and do refueling of my chaser, or I do post-mission disposal, or I just grab another target and then remove myself as a chaser. Having now we know where we want to go. I told you I also need the design to finalize the simulation. So we have the SL8 rocket body, and from there I derived the kit, the design for the kit. It fits into this nozzle here, and it will attach by opening up the top and have a stable fixed connection. You see here the functional architecture of the chaser of address A, and the most important part is that it works on robotic arms. It has two because it has to handle the kit and it has to handle the target. It has visual light cameras and time-of-flight cameras for relative observation and movement. This is the rough idea how it will look at the end. So having that all said, we know how heavy our target is, we know how heavy we are, we can finally think about simulating all this. But we need to do some considerations. We have those parameters, as I said. We also have to think about operational specifications. Saying that, well, I have those visual light camera and the time of flight camera, and I know they don't like shadow, and they don't like too bright sunlight or too bright reflection. So the time I can operate them limits the whole orbit of 104 minutes to about 52 minutes. Knowing again that the algorithm takes 130 minutes to calculate the movement of the target, I will at least need three periods to finalize my calculations. This is just one example for orbital specifications. When I've done that, I can go to my dynamics, see what kind of equations I do for relative motion, do the transformation of the coordinate systems. I also used an optimizer developed by a university, which optimizes for fuel consumption and brings out an approach trajectory. And now here comes the failure implementation. So either it works, I have a successful rendezvous and docking, or there's a failure during the approach. Then the system has to start handling the failure. If it's just an anomaly, it can just process or restart the whole approach trajectory. If the failure ends up being really, difficult, I should abort because I really don't want to have those two objects collide. I did a little bit more consideration about the orbital dynamics. You see here there's two objects behind each other. So on x-axis they are flying, they're orbiting together. And you see on top the exact movement performed numerically, and you see what kind of derivation I have if I use the Closey-Walsh equations. It's about 0.6% off what I actually am, where I actually should be. And then I have a colleague that did some mathematical, he did some more mathematical input into the whole system, and he derived orbits for small elliptical orbits, saying that the eccentricity shouldn't be more than 0.1, and you have a much higher accuracy here. It's about, in average, 100 times more accurate. If you now add here velocity, relative velocity, you see here they get all the Closey-Walsh equations. They increase in getting off his as well, Mr. Idle's, but they're as well much more accurate than the ones before. However, so far I have not implemented them, but this could be done in a later stage. I can finally now show you the approach. You see here the blue, the red, and the blue line, the blue, the green, and the red line in the target. You also see that I've modelized them as a cylinder. It's easier for now. We can adjust that later. And you also see those docking points. The tripods are the docking points, and the yellow lines show how the docking point moves during the approach, which again is the bright blue line. And it's a successful approach. They do meet here. However, if we have the problem that there's a failure, I pre-calculated the abort trajectory, and it either goes back to the starting point, or it aborts. And it goes around. Those trajectories are based on a safety area and fuel consumption. We are finally at the conclusion and future work. So I'll give you a summary again. The ultimate goal was to stabilize the low Earth orbit by actively removed space debris. And the goal of the paper is to support this research through the development of this simulation. We achieved the mission, concept, and design, And we had a first shot of the simulation. Well, you might have recognized that the autonomy doesn't decide yet what to do. And of course, while implementing that, there will be more things to do. So thank you very much for your time. And I'm open for questions now.
Yes, go ahead.
Most rocket bodies over time start to tumble or have very complex motions. How are you going to handle approaching an object with a complex motion?
You're right, but there's I read a paper, or two papers, that were observing those rocket bodies. Actually, they observed Ariane rocket bodies, and they figured out after some time in space, the rocket bodies, they do not tumble anymore that strongly. So you have a maximum tumble rate of 2 degrees per second, I think, yeah? So shouldn't be, yeah, they're not too strongly tumbling. I trust those people that wrote that paper.
Don't trust them too strongly. We've got observations that say that the tumble rates actually change with time, so we should talk. Question?
Yes, one more question about the rocket bodies themselves. How tolerant are your kits to moment of inertia, center of mass, uncertainties? So for instance, if you dock to the nozzle and the center of mass is for various reasons, say 10 centimeters to the left of off center, rather than, you burn with your kit, rather than just accelerating it in a translational manner, you're going to spin it up very quickly.
Yeah, you say I'm going to start.
I'm wondering how tolerant your kits are to uncertainty in the moment of inertia, tensor properties, and the center of mass location.
Okay, so the idea is actually to spin them, to stabilize the whole process by starting a spin, so they don't start this tumble process. Okay. But by attaching them through the nozzle, well, of course, we first have to figure out if it's aligned with the center of mass, and then see how fast we have to start spinning.
Thank you.
Good morning, ladies and gentlemen. Thank you very much for giving me the opportunity to present our research work from the ANU and SERC, which is match template signal processing for continuous wave laser for the purposes of tracking space debris. So there are a number of different ways of tracking space debris. One such method is using laser ranging. In most modern-day laser ranging systems, you send a pulse of light, and you measure the time it takes for this pulse to return back to your telescope after being reflected by the debris. This gives you the propagation delay, and from that you can calculate the range. But we don't want to just track debris, we want to have the ability to maneuver the debris to avoid collision with satellites and even space debris on space debris collision. And how we plan on accomplishing that at SERC is using a continuous wave laser and applying radiation pressure on the debris. And we hope to change the debris' orbit enough to avoid a collision. But this brings up one challenge. You're now using two different lasers, one for tracking and one for maneuvering. This is where our research comes in. We want to have a tracking system that's compatible with your we want to have a ranging system that's compatible with your maneuvering system, tracking and maneuvering simultaneously using the same laser. So first of all, we need to modulate the outgoing laser light. And we plan on utilizing a match filter at the receiver to extract the orbital information such as range, acceleration, and velocity. One such stimulus we can use to modulate our outgoing laser light is pseudorandom noise codes. M sequences of PRN codes have very good autocorrelation property. And what this means is if you have two identical codes, and if they're perfectly aligned or in phase, then the correlation output is going to be extremely large compared to when the two codes are out of phase. Now, this property is pretty good for finding the propagation delay to a target. But from the telescope's point of view, the debris also has a change in distance. It has a velocity and it has an acceleration. And this causes some problems in our integration because we're looking at an entire cone instead of a single pulse. So if we send our modulated laser light, it gets reflected by the debris and comes back to our telescope, we can see that when we compare it with the transmitted code, our received signal has been shifted in time. This is due to the propagation delay. And if we compare it with our locally generated code, the two codes are out of phase. So the correlation output is not going to be very big. But if the debris has a velocity as well, for example, if the debris is moving towards the telescope, now every single bit is arriving at a slightly shorter propagation delay than the previous bit. And this creates a compression effect on the signal. If the debris is moving away from your telescope, then every single bit is arriving at a slightly larger propagation delay. And so this creates a stretching. And if you have acceleration, it changes the rate of compression and stretching you'd see on your signal when we compare it with a locally generated code. All of this will then affect your correlation output and will affect your measurement precision. So we thought, why not we use a batch filter to try and recreate the same condition on your locally generated code and so maximize your correlation output and improve your precision. Now, match filters is not a new technology. It's been widely used in many different fields for many, many years, including in radars, and even the recent detection of gravitational waves. Scientists at LIGO use match filters and with template banks and parameter estimations to not only identify the presence of a signal, a gravitational wave signal, but find out what parameter and what parameter values best match the signal they've detected, and use that information to find out the celestial bodies' properties that generated gravitational waves. So we want to use an idea very similar to that, to our system. So we have our signal coming back at our telescope. We're going to digitize the signal, save that data for the entire time we're tracking the debris, and in post-processing, use a match template to then recreate the same signal that we've detected on our locally generated code. So here's an example of how we kind of picture the match template. So in the example, we're only looking at distance and velocity. So as we change the values as we go through the match template and we change the values of each parameter, for example, if we change the distance, we can see that we're shifting the locally generated code and we're trying to find out where the two codes match up. If we change velocity, in this case, we're compressing the code with our velocity, we want to see which compression, again, best matches our detected signal. And if we do this for every single point on the template, for a signal that's coming back with no noise, so perfect system, that's never going to happen, the correlation output would look like this, where at true values, you get your maximum correlation output. And as you move away from those true values, your correlation output will start reducing. So we're looking for that peak. But before we go into some of the simulation experimental results we've done, there's some system design conditions we need to look into. So of course, receive power is very important. More power, more SNR, better measurement. Chip frequency, that's the rate at which your PRN generator is generating a new output. The width of your chip frequency determines how precise your measurement is going to be. So the higher your chip frequency is, shorter time interval, better precision. Integration time also will affect your measurement. Longer integration time means you have more information on your signal, better suppression of your noise, so better SNR, and also you're more sensitive to all this compression and stretching you see on the code. You also need to have a good detection bandwidth, and of course, noise is very important. All of this affects not only your signal detection, but also your precision. So this is our experimental setup we had in the lab. We have our CW laser, which we send into a Mach center time interferometer, which allows us to amplitude modulate with our PRN codes. We use fibers to kind of have a propagation delay. And between the output of the fiber and our photodetector, we apply these ND filters, which allows us to attenuate the light. So we can look at different receive signal powers. That signal is then digitized by an ADC and saved using an FPGA. This is actually how that setup looks like in the lab. And there are a few parameters we need to consider. So at this chip frequency and ADC frequency, the maximum amount of data we can collect is half a second. So that will be our maximum integration time. We can't do any more because that's the limit of our FPGA, the current FPGA we're using. The second important parameter here is your detector noise equivalent power. In a real application for space debris tracking, we'll use a photodetector that has a lower noise floor, such as an avalanche photodiode, which allows you to detect single photons. But we don't have one of this in our lab, so we got to make do with what we have. So for all simulation experiments, we're going to be using that photodetector. So while we were doing our experimental setup, we did some simulation to see how well our match filter operates in different conditions. So we started off with a really short code, about 1 millisecond. And we modeling our optical setup. So the dominant noise source here is that photodetector I just mentioned. So as we increase, and we're looking at power around about your detector noise flow. So as we increase power, your error in your velocity measurement starts reducing. But even then, at a higher power, it's still pretty bad. So we increase our integration time to 10 milliseconds, and you can see that's improved much more at the same received power. And this kind of tells you the longer you integrate your signal for, the better, less errors you would see in your signal. So just before the conference, we collected some actual experimental data, and we got this plot. And when I saw this, it broke my heart. And I decided to drown my sorrows by going into the hot tub in the Y layer. And after that, an hour later, we went back and looked at the data. And we realized the reason why these two plots don't match up is the signal going into our ADC is extremely weak. So the dominant noise source is ADC noise, which we didn't model into our simulation. So when we go back to Australia into the lab, we'll add an amplifier, retake the measurements, and see if those two lines now overlap. And once we've done that, we'll repeat the experiment for a longer integration time, 10 milliseconds, and see if those two also overlap. So what's next for this topic? What's next for this project? We've got to complete all the experiments I just mentioned. We want to see how well it performs with velocity. And then once we've done that, we want to see how well it performs with acceleration. We want to see how sensitive our match filter is to changes in velocity. But there's one more thing we realized. Modulating a high-powered laser, such as 10 kilowatt laser, at high chip frequencies in megahertz range is extremely difficult. But there's another project that we're working on at the ANU called the optical phase array, where you coherently combine multiple laser emitters to increase your intensity at the far field by controlling the phase of each emitters. From my point of view, since you can control this phase, you can actually change the point where your maximum intensity is going to be. In a way, you can think of it as steering the beam. So this could allow us to amplitude modulate at high frequencies. But we haven't tried it. This is something we're thinking about in the future. And hopefully, by end of this year, we can maybe show that this could work. But if you want to know more about the optical phase array's capability, then I would suggest talking to either Paul Sibley or Lyle Roberts. Both have posters here at this conference. They know more about the system than I do at this point. Thank you.
We have time for a couple of questions.
Hey, this is all in post-processing, so could you, have you got any thoughts on if you could have a feedback loop so that you can continuously track, or is it always going to be in post-processing?
Well, it's going to be all in post-processing. Ideally, you want to have a long integration time as possible. I mean, one way of looking is integrating for the entire time you're tracking the debris, which is going to be difficult if you have a feedback loop because you need to constantly update that. So the longer your integration time is, the better your measurement's going to be. If you integrate it to like infinity, to precision, it's going to be the best it's ever going to be.
This assumes that you have a target already being tracked, perhaps?
Yeah.
Okay.
Yes?
So if the target object is rotating, or maybe this high-speed rotation object, how do you distinguish the change in the received signal to other object?
Well, if I understand it, if the object has in rotation, if it has an effect on the code we've modulated, then if we apply those same effects, what we think those effects would cause on the signal, we can then find out what those rotational properties. But I'm not sure if that's something we could see with our signal. We have not looked into that. We're just looking into distance, velocity, and acceleration at this point.
Actually, I have a question. How long do you see the timeline between going from laboratory experiments into tracking debris that's been
That's a very difficult question to ask. I'm hoping to have the laboratory experiments completed by middle of next year. It's kind of when my PhD ends, so I'm hoping to get results by that. But if the results are good, then maybe because since we're hoping to do a demonstration of debris maneuvering at Cirque in 2 or 3 years' time. So if these results are good and we decide to use this as a tracking system, then yes, we will probably add that on to the system.
We do have time. Another question?
Back to ambiguities, how do you distinguish between range ambiguities and any velocity ambiguities you might have?
Sorry, could you repeat that question?
What do you do with respect to ambiguities? How do you distinguish with respect to range or whatnot?
So it's well, okay, if I understand the question correctly, you'd have multiple, in a real system, you'd have multiple peaks, which because of the different velocity or different range would give you those peaks. But as we go into a finer and finer measurement around those peaks, we can then see what are the true values. And we can say, okay, those results make sense. This is what we expect the orbit to be or not.
Okay, so you use initial knowledge to determine which peak would be the right one?
Well, we have some basic information of the debris. For lasers, we can't track new objects because the field of view is too narrow. So we already need some idea where the debris is going to be. So we have that information. We're just trying to improve on the already known data. Thank you.
Thank you. So, good morning, everyone. I'm going to present a work we started a few months ago in the University of New South Wales in Australia, Canberra based. Yeah, that is based on the use of small telescopes to try to improve detection characteristics and features from geosatellites. Yeah, so the problem is that space surveillance networks need to have a capability to identify geosatellites as best as possible. So we need to find solutions to get a fast identification, and maybe that could be done through the aging of materials that constitute a satellite, or maybe we could even detect attitude of satellites. So that's something that we need to explore. Just to give you a rough idea about the resolution, diffraction limited resolution from a telescope. Yeah, so you can see in the table that even for a big telescope like 10 meters, we will have a diffraction theoretical resolution of 40.339 meters, which is low, but yeah. So there's two solutions traditionally, or not traditionally, but has been using or are being explored. Is the use of larger and larger aperture telescopes, or also optical interferometry, which techniques that are good, but still, I mean, they are in development, and they have like drawbacks, like the atmosphere turbulence that is going to influence these two techniques. So what we have is small telescopes in Canberra, in the ground segment in the space group that I belong to in the University of New South Wales. And we try to find solutions, alternatives to this I gave you before. So you can say there's like 3 techniques to get information from light, reflected light from satellites, passively. Intensity measurements that has been successful and still is a technique that is used and has been used for many years now to detect, for example, tumbling satellites or any other features. You can even detect the spectrum of signals that could give us some, but still some techniques that are in development. We can obtain different things, but still need to be complementary with others. And we have polarimetry. So polarimetry, or use the polarization of light to detect features, is a less used technique. And some authors said that even just 10 years ago, it was a underused technique. And still, that was 10 years ago, but still now is, according to our survey of literature, in terms of looking at resident space objects, it's not something very used. So I found some laboratory results, I found some simulations, and just a few experiments on Sky. So yeah, laboratory results, they basically try to characterize materials that form part of the satellite. And of course, they have different optical signatures of polarization signatures, depending on the material, the angle of reflections and things. Simulations also, some of them are successful. But experiments, according to my survey, I didn't find still a lot of work on that. So we propose ourselves to try to do something with that. So as a first step, because this project started a few months ago, we try to evaluate polarization, passive polarization, as a technique to start information that could be complementary with other techniques or could give us some information that the other techniques, they don't give us. With the possible applications should be identification of satellites, so different things that can be involved there, all right? Just to give you a short introduction, just this slide is, we have a space group in Canberra in the university, around 20, 24 academics, professionals, engineers, and we are going to launch 3, 4 CubeSat during the next few years. So I, with another 2 people, we are form part of a small, the ground, let's say, optical sensors. So that's our job here. Yeah, we have capability using small telescopes to detect different layers, the ISS or CubeSat, like you see in that inverse image. It's a 1G CubeSat, probably a glint, of course, GEO satellite. So as I said before, we are using small. When I say small, I say less than, so the biggest one is the 0.5 meters, 20 inches. And then we go down to amateur telescopes like 0.3, 0.4. So that's what we have and what we are using. So we are lucky because we have, there's one node of the Falcon telescope network from the US Air Force Academy is just operated by us. So we have 1 kilometer away from the campus that is in the right. We have the Falcon telescope network, node Canberra, that is the best asset that we have right now because it has a very nice telescope with a very good tracking system. Is completely, can be remote controlled and operate with taskings, program tasking, so that's the thing. Yeah, so the idea was to use 2 telescopes for this observation. So we have 0.3 meters in the roof of one of our buildings and the 0.5 meters 1 kilometer away. So the setup is something like that. We have looking at geo belt passively from the light, and we have the 0.5 meter I told you before, and this is an amateur class telescope, 0.3 meters. So this telescope has connected a local computer, and we can connect remotely through a network to the Falcon telescope. So this involves that we can use both telescopes simultaneously, taking measurements practically at the same time with just the delay of the network. But one of the problems of using different telescopes to look at the same object, we have different diameters, of course, different cameras, field of views, resolution. So we have to do a proper calibration of the system after we, before and after we do the science, we take the science data. So this is just simply the setup we already have in the 0.3 meters telescope. So this 0.3 meters telescope is where we put an optical train with a linear polarizer. In the other one, we just measure the irradiance only measurements. So we are combining measurements from the Falcon telescope, just only the intensity, and we take the polarization measurements with this telescope here. We have simple rotator stage where we put just a couple of lenses to reimage the focal plane of the telescope in the camera, and a linear polarizer in the middle, just to have a collimated beam here. And yeah, this is controlled by the computer, and then we can rotate this stage in increments of 60 degrees and take the camera ready for the next measurement. So this is very simple setup. We already did in this telescope. We follow a process to the acquisition and processing of the images is just we follow the normal procedure in astronomy, which is taking bias, dark, and flat fields because we have a rotation stage, and we are measuring the polarization of light at different angles. We need to take also measurements of bias, dark, and flat fields at these angles, different angles. So basically, in the first stage, we need to calibrate cameras just to find let's say a right point in the exposure time. We need to put both cameras, different exposure times, to get the approximately same dynamic range in the cameras of both telescopes. Yeah, and the acquisition process is just take images, science images, and then rotate the polarizer. Excuse me. And finally, use this data reduction to the processing and obtain the light curve. So what we want to obtain finally is the light curve, because this is where we are supposed to have that information included. Yeah, so we take a first set of experimental data, and I just advance you that is not conclusive. We didn't get any information that at this stage could provide us with some characteristics that we could say, okay, this is this satellite because this has this polarization curve, or we can use this information for that. But that's the first step, and we need to continue working on that. But I was going to show you just very quickly. So we investigated three GEO satellites that are close to our longitude. So this is a cluster of 2 Australian satellites, Optus, D3 and C1. Yeah, you just can see up there the light curve after the a glint after the occultation behind the Earth, because at this time of the year we have the equinox, so we have this period of time. And we also investigate another satellite, the NSS-9, and you can see here at the first stage, excuse me. So this brown curve is the light curve obtained with the Falcon telescope. So it's just intensity. And these 3 lines here, red, green, and blue, are the polarization signatures at different 0, 60, and 120 degrees. So from these 3 curves, we will obtain the Stokes parameters, and then finally the degree of polarization of the light. Just to show you that, of course, the curves make sense. So because we are looking at the same object, maybe some difference in delays or something, but that's the general trend. Then we have the Optus D3. So again, we have same behavior in light curves from one satellite to the other. We try to investigate satellites from the same launch year, maybe with same bus, just to see if we can see any difference between different years, and also between different bus configurations. So that's what we intend to do. So here we just, you can see a time lapse of zoom. This is in the 0.3 meters, and this is the 0.5 meters time lapse. Yeah, and the Optus C1 pretty much the same. This has a bigger solar panels, bigger bus, but yeah, we can see some difference here, but still we need to explore what is exactly this, and we need to be more recurrent and do more repetitive with experiments. So just to be finishing, I think, we have obtained the Stokes parameter from those 3 light curves that I told you before. And that's for the NSS-9. So in the top, we see S0, which is the intensity only created by the Falcon, and this is the intensity only measurement created integrating the time in the 0.3 meters. And below, we have S1, S2. S1 is the inclination of the light to come in horizontal polarized than vertical polarized, and this is 45 degrees minus 45 degrees. And this is the degree of polarization. So this, you can see the values are very low, so this doesn't give at this stage any sensible information. Same thing with this one. This is the Optus D3. What we can see here is we have a relation between this and this 5 times bigger approximately, but you can see here and here we have a different degree of polarization. So we have like 5 or 6 times bigger. So this means that this satellite that is collocated with this one, maybe they have a different polarization signature at this moment. But yeah, so that's a preliminary result that we need to explore. Pretty much the same for the other day. That's the same cluster, another day of observation. After eclipse, in this case, we really don't see any important features here about because these values are really low at this stage. So just to conclude, so for this project, we have we want to explore this capability of polarization of light, but we consider still we shouldn't just stop because we haven't had any definite results yet. But what we need to do probably is increase resolution, because we have just mechanical thing. It's just we need to move the rotator stage, take some time, and then we have a exposure time between 3 to 10 seconds, depending on the satellite we are looking at the time of the night. And we want to also try different types of polarization, and of course make a longer run of observation. So from sunset to so the whole night, because these runs that you see before was around 2-3 hours of observation. So we don't consider that it still is good enough to say, okay, we have a system that is not working, or we need to keep working in this stuff. So that's it for. Thank you very much. Any questions?
We do have time for one question. Anyone has a question? If not, I'll take the chair's prerogative and ask you the difference that you saw in the polarization of those two spacecraft. What does that tell you physically?
Physically means that the light is more polarized in one direction than the other. So this means that maybe one of the satellites at this stage has the angle of reflection with the sun is different. So we can, ideally, we could detect any altitude detection of that. And also, we can give that information. So it's three types of information that could deduce from that. But we need to know which is which. Other kind is aging of material. So depending on the aging, because in the space, maybe one of them was 2003, the other one's 2009. So depending on the aging of materials, the polarization is going to be changing also. So maybe we could associate this change in polarization with the age, with the date it was launched. And also the material. So the material have different polarization. So it's different sources that can create this problem. We didn't identify which is the source of the cause of this change. But yeah, so we are working on that.
Okay, yeah, that'll be interesting. Thank you very much.
Thank you.
Our next speaker is from the United States. It's John McGraw, and he'll be talking about multiple observing modes for wide-field optical surveillance of geospace. John?
Greetings, everybody. Today, I would like to talk to you about something that we're doing as J.T. McGraw and Associates. There's a whole 3 of us working on a project that we hope to be transformative with respect to optical, ground-based observations leading to space surveillance. So we believe we have the possibility of a bit of a paradigm shift. Our view of what happens when people use optical telescopes on the ground to observe space is that the targets tend to be selected, pre-selected. And so the net result is that we are missing a capability that we've developed for extremely wide field imaging from the ground. So what we're looking at is affordable, that comes first, not only because it has an A, persistent, wide field, uncued, responsive optical imagery of space. And the two images are there just simply to point out that here is the geobelt we can do, 40,000 kilometers. Here is Aegis, we can do LEO. We believe that there really is a purpose to surveillance of space, and oftentimes we miss the idea of working to some kind of a definition or a goal. The purpose of surveillance of space, in our estimation, is to detect and monitor the behavior, activities, or other changing characteristics of Earth-orbiting objects for the purpose of influencing, managing, directing, or protecting them. So there is a real goal in mind here. And the other asset that we believe is not fully exploited is the idea that true surveillance is really driven by data. So we believe there's no sense in doing anything less than persistent surveillance in this case. So we have examples of wide field of view surveillance that is accomplished on Earth. Here we're using the example of a parking lot. If you have a small targeted field of view, you get to see this car. You can see it parked in its slot. Everything is wonderful. But if you have the wider field of view, you see not only that that car is legally parked, but you see that there are no scofflaws in the fire lane. The volume of data accessible from that large wide field image is just simply far greater than that. And the effort one goes to get the wide field image is not appreciably different from that of the single automobile. So we've got a large number of topics to cover here, and we're going to go through these one by one at a time. The first is that uncued surveillance enables discovery of and orbital characterization of new faint objects as well as detecting and characterizing cataloged objects. Uncued capability does not preclude directed observations, including things like launch for insertion, staring mode at potential conjunctions, targets of opportunity, whatever you dream up. There's no downside to relative to cued confirmation for these kinds of wide field observations. Uncued surveillance provides all these products. And our techniques also provide accurate astrometry, referenced currently to UCAC4, real-time trajectories, including handoff capability, which we have already demonstrated in a same pass detection and then handoff to a third telescope that followed up on it. We can follow launch, LEO to beyond geosurveillance, all to good measure. So what we're going to do is touch on some of these topics. So current optical surveillance are typically object-driven, and positions for objects of interest sent to telescopes for confirming and updating observations is one way of operating. It's common, but this mode of surveillance doesn't really take full advantage of wide field sensors. Our imaging techniques allow passive generation of mosaicked all-sky images or any other useful image configuration, such as a rectangular survey of the geobelt. And from these images, we derive position, motion, and brightness for every object above some canonical signal-to-noise ratio, which we choose to be 6 as sort of the industry standard for now. True surveillance, in our opinion, is data-driven and anticipatory. The sensor array we're describing here can be deployed at multiple sites worldwide because they really are affordable and they are replicable. And to be clear about this, the observations we're discussing are all made with a Celestron 14-inch telescope with a detector suite. The telescope is mounted on a software BEASC torus mount, And this is all very straightforward to do and keeps costs down. And so you pay no penalty for wide field. You pay no penalty for replication. So the fundamental elements that we are trying to address here are security in the sense of persistent surveillance and intelligence. Security depends upon the completeness of surveillance of the volume of the activity, and surveillance of space in turn requires affordable persistence with multiple sensor types. The constraints and solutions to the technical problems that we have to deal with detector readout noise and sky background. And for those of you who potentially recognize my day job, one of the things that we teach religiously is that when making measurements, measure the noise and you get the signal for free. And so we concentrate a great deal on ensuring that we know how the propagation of noise in these observations actually occurs. And Pete Zimmer, in the next talk, will describe this in some detail. Of course, whenever you're trying to do all-sky survey, the first thing that everybody thinks about is actually the easiest to solve, which is, well, what about bad weather? And the answer is that if your telescopes and sensors are sufficiently robust and inexpensive, you buy another one and you put it nearby in a different weather system. And you can do this ad infinitum, but put 2 or 3 detectors operating in sort of the same angular domain on Earth will work just fine. In our observations, we have decided to stare and track at the sidereal rate. And the reason we're doing that is several-fold. The first is having nice point spread functions for stars provides an angular reference on the sky, which relative to the UCAT catalog or future very large astrometric catalogs, can give us good angular measure anywhere we look on the sky. At the same time, these catalogs provide radiometric measurements, including as a function of time. One of the hallmarks of the wide field surveys that we implement are that the characteristic observing times are of the order a second to a few seconds. And signal to noise ratio is built by adding data as necessary or overlapping data as necessary. Cost is always a constraint. And for optical surveillance of space, this drives in large measure from good judgment about vendors and sources of sensor systems. JTMA uses COTS hardware and software whenever possible. The components, however, are always implemented using our own optical designs, operated under our own physical models, and data are acquired and analyzed with our own software. Much of the optical SOS, the surveillance of space imagery done from Earth, utilizes classical astronomical telescopes designed principally to resolve the seeing profile on a given night, resulting in a smaller field of view from telescopes with rather high F ratios. Typical astronomical telescopes thus have sub-arcsecond pixel resolution and fields of view measured in arc minutes on the sky. The predominant telescopes used today for ground-based surveillance of space remain higher F ratio telescopes and with somewhat smaller fields of view consequently. These telescopes are typically employed to provide pointed observations and confirmation of the presence of an orbiting object and to improve its optical elements. We contend that both survey and pointed observations are in fact relevant for surveillance of space. The paradigm shift that we would like to bring about is that instead of thinking of surveillance of space of optical, in the optical as a large number of discontinuous postage stamps as provided by classical astronomical telescopes, that we do large area surveys because there are no downsides to doing so. The Wide Field Survey attains the same or fainter limiting magnitude than the classical astronomical telescope observations. All of the classical cued observations are included in the Wide Field data set, plus everything we didn't know existed there, or objects simply not on the priority observing list for the cued mode observations. We obtain a broader vision of space with which to accomplish true surveillance of space. Now, what did we just see? Well, it was a bunch of boring boxes, but that series of boxes that were being built for you was a simulation in real time of a geo survey. It was done with a 14-inch telescope tracking at sidereal rate. It used a scientific CMOS device of but 2K by 2K pixels, and each of the images covered 1.8 by 1.8 degrees on the sky, or 3.5 degrees per exposure. Each integration was 6.4 seconds, with an added 3-second slew and settle time. And this is actually rather conservative. Magnitudes are misleading in most cases when talking about detection limits for surveillance of space. But what we will quote is 17 plus magnitudes at GEO and 14 plus magnitudes at LEO, and this again is conservative. What we saw generated were 40 raster images, 142 square degrees on the sky. The canonical US CONUS GEO is 30 degrees in the north-south direction by 120 degrees in RA, 3,600 square degrees of the sky. We just saw the result of one of these inexpensive telescopes surveying 4% of CONUS GEO in 6.4 minutes. Satellites with V magnitudes greater than 17.3 would be detected and uncued in terms of what we actually see. This means that in 2.7 hours, that one telescope with one detector can survey all of CONUS. So even with overheads for pointing, we end up being able to survey all of CONUS twice from one site location, and we're prepared to do this right now from New Mexico. Thank you.
Yes, go ahead.
Hi, John. What you've basically just showed us is a form of an optical fence. All fences have leaks. And by that I mean when you're looking somewhere else, somebody is doing something else where you're not looking. Have you done any analysis on the susceptibility of your technique to such leaks?
Well, what we showed here was what happens when you have one 14-inch telescope. So if you want something that doesn't leak, you plug the holes. Now, there are large numbers of decisions that have to be made about how one actually accomplishes surveillance of space. We're hoping that what we've just discussed is a new way of looking at things so that these discussions can be carried out. How important is it to have overlapping observations? How important is it to have one telescope doing 2 whacks at CONUS all at one time? I mean, there are some obvious answers to these things, but the brutal fact of the matter is the only way you're going to see things continuously is to look at them continuously. And that's why it's so important to have affordable sensors.
Thank you very much. The last talk before lunch. What an envious place to be. Pete Zimmer from the United States giving a talk about the affordable wide-field optical space surveillance using CMOS and GPUs. Pete?
All right, thank you, Sue, and thanks for you guys staying before lunch because I understand the temptation of leaving. So hopefully I can keep you guys entertained. So as Sue said, I am Pete Zimmer. I'm listed here under J.T. McGraw & Associates, LLC as research scientist, but You could probably put associate number 2 down there, and that would probably be the appropriate title there. So I'm going to continue on with what John said about affordable wide-field optical space surveillance using SCMOS and GPUs. And there's probably maybe still be someone in the audience who asked me a question about using SCMOS and the techniques that we were using in previous years, and I think I kind of poo-pooed that a little bit. And all I can say is I've now sort of seen the light. So to whomever that was, I apologize, 2 years too late, but I came around. And actually, you can see there's actually a video animated back there, and that's a real-time, basically, display of what, something that's sort of a LEO object moving through our field of view looks like. So this stuff actually works pretty nicely. So the upshot here is that our new SCMOS technology actually just erupted sort of on the market in the last 6 months. And I'll tell you what makes those things actually new and unique and why it's valuable to space surveillance. But with this, we can do things like, as John said, fainter than 17th magnitude for geo-rate objects under moderately bright sky conditions. That's roughly 60 centimeter object at geo, with all the usual hand waving on this stuff. Fainter than about 14th magnitude for LEO objects, which comes out to be about 10 centimeters at 1,000 kilometers with, again, the usual hand wavy things. And that's with a 0.35 meter class telescope. Here's what that looks like. This is our first system that we just set up in New Mexico. It's a 14-inch Celestron with a Tucson SCMOS camera on the front of it. The roll-off roof observatory, and you can see there's a satellite image that shows what that looks like there, tucked behind John's house. So the first thing that was a real shock with this particular sensor is that it's big. Now, it's not big as CCDs go, but it's big as SCMOS go. And so this is a 22 millimeter by 22 millimeter active area. So that's actually appreciable for an SCMOS camera. The previous ones that people had been selling were a little bit bigger than half that on each side. So now we can actually cover some sky with these things, because if you don't have a big sensor, you actually can't cover the sky. So you need that for efficient sky coverage. And there are even larger sensors that are available and some other ones that are on the horizon. And I'm happy to talk to you guys about what I know about that offline. But the big thing here is backside illumination. And this was a big deal when it came out with CCDs, some decades ago. So backside illumination in itself is not any big deal. But backside illumination on a SCMOS camera, that's actually a big SCMOS camera that is also backside illuminated, that got my attention. And I went, aha, we can crack open space surveillance with this detector. So you can see here I've got several quantum efficiency curves plotted. The one that's at the very bottom, that little sad Kodak curve, I mean, I say sad, I love those cameras. I did so much work with those. But I haven't touched them since. And you can see that just that difference in sensitivity curves between that red curve, which is our SCMOS curve, and the blue curve, that's the Kodak front side illuminated inner line sensor, almost instantly picks you up a magnitude in sensitivity, just like that, boom. And when we first took images with this camera, they just popped out. The sky just came out in a way that I hadn't ever seen before on a telescope of this size. It's great. The second part of this SCMOS thing that everybody knows about, or maybe everybody knows about, everybody should know about, is read noise. And instead of our other cameras that had read noise that were 10 or 11 electrons, we're now talking down at 1 electron, 1.5 electrons, 2 electrons. And I've got plotted there the real distribution of read noise for the pixels on our sensor that we have. That's measured from a series of, can't really take a bias image with these things, but these are essentially as fast as you can read them out in the dark. And you get something that, their spec is 1.5, we're getting about 2.1. It's an early version of this sensor, so I'm gonna live with that. And it's important to point out, though, that unlike CCDs that have 1 or 2 or maybe 4, some a lot more than that, but they have a handful of amplifiers on them. In this case, the SCMOS architecture, each pixel you need to treat like its own detector. So that's why you see the read noise is actually a curve. It's, the blue line is actually showing you the histogram of read noise, and the red line is actually showing you the cumulative histogram. And so if you actually really want to look at what the effective read noise is, you kind of actually need to look out at the tail of that, it's kind of like a log normal curve, basically. But the other thing that's really cool about this, unlike CCDs, is that 1.5 to 2 electrons of read noise actually operates all the way through up to 20 frames a second. We normally run at about 10 for various signal-to-noise reasons, but the rapid readout at that low read noise is critical. The there's a downside, and this is one of the things that originally caused me to kind of crap on, sorry, can I say crap? I'm sorry. Originally made me downplay SCMOS detectors. They have a large amount of what people would describe as either fixed pattern noise, or it's just each pixel, again, being its own detector essentially, has its own response and its own, essentially zero level involved. And you have to do something about that. Because if you look at that sort of that top little image over there, so I stacked up 64 frames and did a sum on those. And you can see there's some stars in those images, so that's real data. And there's a lot of structure in that background, right? That's just there. And the reason why I did the sum is just so that you can really see that above the read noise and above the sky noise. But it's there, it's at a low level. It can hide a little bit in the noise from the sky, but it's there. But if you do some actual, not terribly, horrendous corrections, sort of, I would call them analogous to your CCD bias flat field kind of corrections, you get what you're seeing there in the lower frame, which is a nice clean frame. And you might go, oh, hey, Pete, I think you might be fooling me there because did you play with that color scale? And the answer is, yeah, okay, you got me. I played with the color scale. It's actually enhanced by a factor of 3 in the lower frame. So you're actually showing an even much lower dynamic range, essentially, in that background. You can clean it up very, very nicely without wrecking the actual noise distribution that those pixels are giving you in the first place, which is also critical to this operation. It does cost you some extra processing time, but hey, we'll talk about processing time in a second here. Because now when you go to 10 frames a second, you start having to accumulate a lot of data, and you have to do stuff with that. And if you don't actually process it in real time, you will just be drowning in it. You will have no space for it. So you have to do real-time processing with this, because 400 gigabytes an hour, that adds up, even today. So, as you might guess, GPUs, again, here are to the rescue, and that's what we do. And the good news is that they're still keeping up with Moore's Law. Our current commodity GPUs that we just got, they just came out in August, they're about 60% faster than the ones that I got the previous August and told you about last year. So 60% increase in a year, I'm just going to pretend that that's going to keep doing that forever, right? That will happen. They've got big RAM buffers, they've got low power consumption, and the combination of all this allows for a very large parameter search space for detection of things sitting in this very rich data set. So baseline system, as I said, 14-inch Celestron with running at f1.9. It images a 1.8 degree by 1.8 degree field of view down onto this detector. We run at 10 frames per second, 2 electrons of read noise, and it's essentially a really good match of optical system to the detector. And what we love is that there's no dead time, but you accumulate lots and lots of images. So here's my first light image, really. And it's not really truly my first light image, but it was the first actual object that came through about 5 minutes after I turned the thing on. That actually was an interesting object in that I knew what it was, and I could see it, and it had a catalog, a catalog match. So what I'm showing you is there is one single 0.1 second exposure. Now everything has been cleaned out of this one. It's about a magnitude 11.6. It's going 1,860 arc seconds per second, and I got it at a signal to noise of 34 in one frame. And you can see the along the track there, light curve is plotted down below. So it's a nice, solid, clean detection. I do actually have enough time to do this. So this is just a little bit of an aside. This is a hobby horse of mine, trailing loss. What I did was to simulate our older system, which was taking images every second. I co-added 10 of these frames just together to see what happens. And then I scaled this image here so that you actually match the noise in the same way. So basically, we're seeing things from about 1 sigma clipped up to about 6 sigma of the actual background noise. And what you can see is that you add up 10 frames, and it's still a clear streak. You can still measure that, but you'll see that the individual per pixel signal to noise went down, as you would expect from trailing loss, right? The noise is growing underneath this streak if you're exposing for too long, because the streak, the object is only contributing as it moves over those pixels. And in the upper frame, I now have the projected, sort of extracted along the streak light curve. And you can see the blue curve is now for this coad, and the orange curve is the one that I just showed you from the previous frame, the single frame. And it's noisier, obviously, and you can see that the effect of trailing loss is now that your actual per pixel noise has gone up, which you expect it should. It's all in the sky background. And so trailing loss, though, is a bummer. And it's a bummer because if you go ahead and try to extract the full signal to noise along the streak, whether it's the short streak or the long streak, The orange shows the extracted along the streak signal to noise that you get. And it peaks, you start out at the beginning of the streak and it peaks up and it reaches a maximum when you hit the end of the streak. And then it drops down as you start getting into the noise again. The blue curve is what happens when you do it on the long streak. For 10 seconds of the image, it grows and it grows and it grows the way you'd expect, but it peaks up. But it does not peak up at the square root of 10 times that single exposure. That's what you would expect from a point source object. So this is the reason why framing really fast is a really big gain. And if you can frame fast and keep your read noise low and keep your sensitivity high, it's win, win, win. That's why these detectors are a big deal. So just to go on about this particular detection, so the thing that made me interested in it is it's got a known published radar cross-section of 0.08 meters squared. So that's about, people who do radar, you can check my math because I didn't really do algebra that well. So I think that's a 32 centimeter diameter, and you can, I guess that's bigger than that. At about a range of about 800 kilometers. So that's a reasonably large target actually in LEO, but that's good because I detected it and it was kind of bright. And so you can estimate what you would get as a magnitude for that thing out there at its range, and it ends up being about 11.1. If you do, again, all these same hand wavies, it's a sphere, it's that size and diameter, and it has a reflectivity of 12%. So a dark gray ball that's 32 centimeters in size. That's estimated about 11.1. I measured it about 11.4. So that's a little bit further away than I usually get when I do comparisons between radar cross-section and measured magnitude, but it's close enough that I'm not going to argue too much about that. But since I detected that thing at 30 sigma, I can actually estimate what my real limiting signal, what my 6 sigma detection is now 13.2 or a 15 centimeter object at that same thing. And that's in 1/10 of a second. And oh, by the way, I took this last week and it was the full moon. So it's the worst case scenario for background. So obviously there's a lot more information here that can be extracted. And there's a little, the upshot here on the detection limits, and this is actually running the real data through our processing pipeline, and we do some further processing. We don't just do single images, we do a lot more other things with it that I can't tell you about, but we can actually predict what we would actually be able to see as our detection limits. With uncued LEO survey mode, that means you just sort of point at stars and you let things move through. We're down in sort of the 14 range. For cued LEO, where we know a little bit more about it and can make some educated guesses in advance, then we're more in the 15 range, which is down to about 6 centimeters at 1,000 kilometers. Uncued GEO survey, about 17.2 or so, which is about 60 centimeters. Again, this is the 14-inch telescope. We're a little bit limited by light gathering power. But that's, again, at a rate that's moving at 1,000 square degrees per hour, roughly, that we can survey. And if you want to concentrate on a particular area, we can actually make that limit a lot fainter. And there will be considerable improvements when we actually use this under dark sky. So again, this is based on the light data with the full moon. So where this is going, as John mentioned, is we're talking about global networks of observatories, each with multiple small telescopes. They can support multiple missions, whether it's cued, uncued, some sort of hybrid thing, neighborhood watch, you name it, we want to talk to you about it. We can support it in LEO, MEO, GEO, HEO, GTO. If you've got other acronyms, I'm sure there's no lack of acronyms. So deployable systems, they're small. We can actually build these things very quickly. And they can rapidly reconstruct capabilities should something bad happen. And rapid wide field detection with a high duty cycle means more collecting time on the sky and cost effectiveness. So we're working very hard to approach the fundamental detection limits. There's only so much we can do with how much light comes from the sky and what the atmosphere does to it. But we want to get every single little bit out of it. So thank you.
Do we have any questions? Yes?
Oh, thank you, Peter. I'm probably going to become a CMOS believer now.
All right.
Can you please comment on linearity of the detector?
I actually can't comment on the linearity of the detector. So as you'll notice, my mission here is detectivity. And I haven't had a chance to actually do real good photometry with this thing. It's on the list of things to do, but there's certain communities that are interested in that, but the ones that I'm sort of tailored to right now, this is how I get food. So
thank you.
So, do you have a quick question?
Yeah, it should be quick.
Great.
So
Go.
Peter, I liked your presentation. One question I had was related to the structure of the CMOS detector. And
Yes.
You've got this background pattern, and so your noise is varying, and you're also looking at extended streaks. And I was wondering, are you able to properly account for that in your signal-to-noise estimation?
Yes. So all of my signal-to-noise estimations are based on measured noise. Okay? That's a critical thing. You have to measure, as John said in his previous thing, you measure the noise and your signal comes for free. That's our philosophy, and that's not just our philosophy, that's what we do. So in each and every case, you don't get the same detectivity in this part of the detector or this part of the detector. And what I didn't say about the cleanup process is there are, that pixel distribution in read noise, there are some pixels that have 30, 40, 100 electrons of read noise. Well, we know where they are. It's pretty stable. So just get rid of them. Don't pay any attention to them.